In this video, we'll talk about vectors, and the first thing that we need to discuss is the idea of what a vector would be. A vector is a quantity that has both direction and magnitude. And magnitude is another word for the length of the vector. Now, looking at this example, the point P there, that is your initial point, and point Q is your terminal point. Vectors are usually noted by using an arrow symbol, and notice that's what you have over these, or you can have your boldface letter. Now, when we're finding the magnitude of a vector, we are going to use our distance formula because we have 2 points here, and so the length of that vector, or the magnitude of the vector, can be found by using our traditional distance formula. So we're going to say x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So when we're looking at our vectors, in number 1, since we're asked to find the magnitude of each, then we would note that we have the magnitude of AB is going to be noted by the square root, and we're going to have negative 7 minus 8 all squared plus negative 2 plus 4 all squared. And so here we're going to end up with the square root of 229. On number 2, the magnitude of vector RS can be found by doing the distance formula. And again, we're going to look at the difference of our x's. So we're going to have 5 minus a negative 3 all squared plus 6 minus 10 all squared. And so the magnitude of vector RS is going to be the square root of 80. Okay, looking at number 3. Again, same process, so we're looking at the magnitude of vector PQ. And we're going to have the square root of, we're going to have 2 minus a negative 8, so 2 plus 8 all squared, plus negative 9 minus 6 all squared. And so that's going to give us the square root of 325. And number 4, we're going to have, again, magnitude of EF is noted by the square root of negative 6 minus a negative 1, so negative 6 plus 1 all squared, plus, and then negative 7 minus a negative 5 all squared. And so we're going to end up with the square root of 29. Okay, now when we talk about a zero vector is a vector with a magnitude of 0. So in other words, when you've done your distance formula, you ended up with 0. Now we also have some different ways we can classify our vectors. And to classify those, the first one we would have would be parallel vectors. In other words, here we have the same or opposite direction, but not necessarily the same magnitude. So we could say this is vector A, and then we could have vector B down here, and we would say vector A is parallel to vector B. Now, equivalent vectors, that means these vectors are pointed in the same direction and they have the same magnitude. So let's call this vector M, and this is vector N. Then we would say that vector M is equivalent to vector N. And then if we talk about opposite vectors, well then opposite vectors, we're going to have the same magnitude, so we're going to have the same length, but they're going in opposite directions. So if we called this vector A and this one down here vector B, then we would say that vector A is equal to the opposite of vector B. Now looking at that, and now we're going to compare our vectors, and we need to first in part 5 is to compare vector A to vector E. So here's vector E, here's vector A, and those look like they have the same magnitude, but they're going in different directions, so these vectors are going to be opposites. Now number 6, we've got vector I and vector F. So vector I and then vector F. Notice they look like they have the same magnitude and same direction, so these are going to be equal. Then we have vector D and vector E. So vector E is here, vector D is there. So vector D and E, notice that they look like they're going in the same or opposite direction, but not necessarily the same magnitude. So for vectors D and E, we're going to call those parallel. Now let's look at vectors B and G. So vectors B going this way and vector G going this way. Now those, even though they look like they might have the same magnitude, they're not going in the same or opposite direction there. They're going completely different. So this one would actually be none of those. And now let's look at vector C and vector H. Vector C compared to vector H, well, those look like they are running opposite. So that is going to be opposite. Okay, and for this one, we're going to prove that vectors are equivalent. And notice that what we have to do is use the distance formula to show that they have the same magnitude. And then we're going to use our slope formula to show that they have the same direction. So the first thing we need to check is going to be the magnitude of AB. And the magnitude of AB, we're going to have -2 minus a -6 plus, and then we're going to have 3 minus a -7. And so our magnitude here is going to end up being the square root of 116. And now let's find the slope of AB. So the slope for AB, and this time remember our slope formula, I'm going to put it over here to the side. That slope formula is going to be y2 minus y1 over x2 minus x1. That is your slope formula. So our slope here for AB, we're going to have 3 plus 7 over -2 plus 6. And so our slope there is going to be 10 over 4. All right, now let's go investigate the other vector. So now we have vector CD. We're looking at that magnitude, and that's going to be the square root of 6 minus 2 all squared plus 0 minus a -10 all squared. So that's going to give me a magnitude of 116. And now let's look at the slope for CD. So we're going to look at that slope. We're going to have 0 plus 10 over 6 minus 2. And notice that is also going to give me the same slope. So notice we have the same magnitude and the same slope. And so that is going to mean that these are equivalent. Now by that same process, number 11, we need to again examine these. So we're going to look at the magnitude of vector AB. And so we're going to have the square root of 6 minus 2 all squared plus -14 plus 2 all squared. And so that magnitude is going to be the square root of 160. We also need to look at the slope of AB. And the slope of AB, we're going to have negative 14 plus 2 over 6 minus 2. And so that's going to give me negative 12 over 4. Now let's examine the other vector. So magnitude of vector CD is going to be the square root of 1 plus 3 all squared plus 4 plus 8 all squared. And so again we get the square root of 160. So now let's look at the slope of CD. The slope of CD, we're going to have 4 plus 8 over 1 plus 3. And so that's going to give me a positive 12 over 4. So our slope is different on this one, so these vectors would not be equivalent. Okay, now we're going to look at a graphical approach. The first thing that we're going to talk about is a vector being in standard position, and that's going to be when the initial point of the vector is at the origin. All right, and so notice that when a vector is in standard position with a terminal point AB, then the component form of vector V is now going to look like A comma B. That's going to be your component form. And then the magnitude and direction angle can be found when we're in the component form by just looking at the square root for the magnitude of A squared plus B squared. And then your direction angle, you're going to find that by setting up the trig ratio. Tangent of theta equals B over A. And do keep in mind that is your opposite over your adjacent. Alright, so for this first part in finding our magnitude and direction angle, it's going to be a bit easier since we are in component form. So the magnitude of vector R is going to be the square root of 7 squared plus 24 squared. And if we put that together, we're going to get the square root of 625, which is a nice, neat 25. Now, what we're going to do to find our direction angle, we're going to sketch this. Notice that our changing x's is over here at 7, and our changing y's way up here at 24. And so what we're going to do is plot this as a point, and we're going to connect it and make a right triangle from here. And so our theta is going to be sitting right there. That's the theta that we will be solving for. So when we do that, keep in mind that this side length here was 7, this side length here was 24. And so this is why we're saying tangent of that angle is going to be opposite over adjacent. Now to actually solve for your theta, you need arctangent or inverse tan of 24 over 7. And when you put that in your calculators, do make sure you're set in degrees. Then that's going to give you theta is 73.74 degrees. And that is your actual direction angle. Notice that direction angle is found between your initial side here and then that terminal side going there. That's going to be your actual direction angle. Now, on number 2, it's going to look a little different. Again, we still need to start out with our magnitude of vector n to be the square root of negative 3 all squared plus negative 1 squared. So I have the square root of 10. But then when we go to sketch this, notice that we will be over in quadrant 3. We would go back 3 and down 1. And again, we're going to sketch our triangle down there. Our theta in question is going to be sitting right there. And do keep in mind that this angle, again, you went back 3 and you went down 1. And so you're going to have tangent of theta is going to be opposite over adjacent. And so really to solve for theta, we need inverse tangent. So inverse tangent of 1/3, and that's going to give us 18.43 degrees. Now we have to think about this a minute and be super careful. Keep in mind that theta that we found is going to be this angle sitting inside here, this angle from here to here. However, the direction angle that I need, keep in mind my initial point needed to be centered right there at the origin. So the actual direction angle I need is all of this. So in order to get that, then I know part of the way around is 180 plus this amount that I've actually found. So the direction angle is actually going to be 180 plus 18.43. So that direction angle is 198.43 degrees. All right, so let's go ahead and find number 3. Again, we need to start out with the magnitude of our vector v, and that's going to be the square root of 8 squared plus 12 squared. And so that's going to give me the square root of 208. Now let's plot this and see what we're going to end up with. So again, here we're going to go over 8, change of 8, and then down 12. So we're going to end up with a nice neat little triangle here. And so our theta is going to sit inside there. And so again, we're going to set this up to be tangent of theta is opposite over adjacent. And so to find theta, we're going to say inverse tangent or arctan of negative 12 over 8. And that's going to give us negative 56.30 or 31, either one you want to do with that. We'll just do 31. All right, so for this one, notice that we got a negative angle, but that's really coming from the quadrant we're in, or if you want to think of it, we went backwards here. This actual angle sitting in here is the 56.31. Now, our direction angle that we need, remember our initial point needs to be sitting at the origin. There's our initial side. So our direction angle is actually all the way around. So what we need to do here is take the entire amount, which is going to be 360 degrees, and then we're going to take off that 56.31. That's going to give us our direction angle of 303.69 degrees. All right, number 4. Again, same process, so we do need to start with the magnitude of vector k, and that's going to be the square root of 121 plus 36. So that's going to give us the square root of 157. Now let's go through and see if we can find our direction angle. We need to go back 11 and up 6, so that's going to put us back here in the second quadrant, and our theta that we saw for is going to be sitting there. So we're going to say for that angle, tangent of theta is going to be 6 over negative 11, and so theta is going to be inverse tan of 6 over negative 11, negative 28.61. And again, keep in mind that negative there, that's really coming from the quadrant you're in. Tangent is negative in the second quadrant. That's this little angle sitting right here. So Again, to find our direction angle though, I need to start here at the origin with my initial point, and that's got to go to here. That's the direction angle that we're looking for. So for this one, I know I go all the way around for 180. So I'm going to take 180 degrees, and I'm going to subtract off this little theta that we just found, which was 28.61 degrees. And then that's going to give me 151.39 degrees. All right, so now let's look at number 5. Number 5, we need the magnitude of vector g. And that magnitude is going to be the square root of 4 plus 64. So that's going to give us the square root of 68. And now, again, we need to plot this to see where we're at. And it looks like we're going to end up down here in quadrant 3. Our theta is going to sit here. We went back 2 and down 8. So we're going to talk about tangent of theta is opposite over adjacent, and so our theta is going to be inverse tangent of 4, and that's going to give us 75.96. And again, that's going to be because we're sitting right here. That's our theta. And again, thinking about our direction angle, we have to start here, our initial side there at the origin, our initial point. And so this whole big angle is our direction angle. So I need to take 180 degrees and add to that 75.96. And so my actual direction angle is 255.96 degrees. All right, and for our last one, again, start out by finding the magnitude of vector A. And that's going to be the square root of 196 plus 25, a squared plus b squared. That's going to give me the square root of 221. And then again, if we plot this one we're going to go over 14, up 5. So we've got something like this. We have 14 and we have 5. There's our theta. And so we're going to say tangent theta is going to be 5 over 14, and so theta is going to be inverse tangent of 5 over 14, and so that's going to give me 19.65 degrees. And this time, if we note again that our initial points here at the origin, we have here, and then up to our terminal, the angle that we found this time is the actual direction angle, so there's nothing to be done to that value. Okay, our next part of this, we need to go through and see how to write a vector with initial point x1, y1, terminal point x2, y2 in component form. So to write a vector in component form is really just talking about the change of x's and the change of y. So we're going to say x2 minus x1, and then comma, and then we're going to say y2 minus y1. That is how you write that in component form. So looking at number 7, to write this in component form, again, you are going to set up and say 6 minus 3, comma, 3 minus 5. And so the component form for vector CD is going to be 3, comma, negative 2. And the same idea over here for vector RS. That component form, you're going to say it's going to be negative 2 minus 5. And then 1 minus 10. So your component form hopefully is going to be super easy for us. Okay, so in problems 9 through 12, we're going to put all of this together now. And notice the first thing they want us to do is find the component form. And that's always a good place to start, because going to component form will make this a lot easier for us. And remember, component form, you're going to look at your difference of your x's. So 4 minus 2, that's going to give us 2. And then 1 minus a negative 9, that's going to give us a 10. So there's our component form. Now for our magnitude, we're going to find the magnitude of MN, and that magnitude is going to be the square root. And again, we're going to use our component form. We're going to have our a squared, or 2 squared, plus 10 squared. And so that's going to give me the square root of 104. So again, square root 104. Now for our direction angle, I do again suggest that we sketch this, and we're going to use our component form. And notice that we're going to go over 2, up 10, so that's a very poorly drawn triangle. And so there's our theta. And notice we're in the first quadrant, so when we find that theta, that is our direction angle. So tangent of theta is going to be opposite over adjacent. And so theta is going to be inverse tangent of really 5. And so theta is going to be 78.69 degrees. So we get 78.69 degrees. All right, moving on to number 10. Again, same process. We're going to go through and find our component form first, and I do encourage you to do so. So that component form first, you're going to say -4 minus 9. And then you're going to say -1 minus a -3. And there's your component form. And again, that's going to make finding the magnitude of AB much easier. You're going to have the square root of 169 plus 4. So you're going to have the square root of 173. And now for your direction angle, it looks like we're going to end up in the second quadrant. You're going to go back 13, up 2. So we have -13 and 2. Keep in mind theta is this angle here. And so we're going to say tangent of theta is going to be opposite over adjacent. And so for this one, theta is going to be equal to inverse tangent of 2 over -13. And that's going to give us, we're going to get -8.75. And again, keep in mind that's the little angle we found, but our actual direction angle is going to be from there to over here. So we're going to have that direction for our direction angle. So to find that, we're going to say all of this, which is 180. And then we're going to take off that 8.75, and that's going to leave us with 171.25 degrees. Okay, number 11, again, starting out with finding our direction angle. That component form, be much easier starting with component form. You're going to have 7 minus 1, and then you're going to have -4 minus 3. Right, now for our magnitude of vector JK, you're going to have the square root of 6 squared plus 7 squared. And so that's going to give you the square root of square root of 85. If I can add, that would help. And now let's find our direction angle. That direction angle, again, if we plot this, it looks like we're going to end up in the fourth quadrant. We went over 6, down 7. Our theta sitting inside here. And so we're going to say tangent of theta equals opposite over adjacent, and theta equals inverse tangent of -7 over 6. So theta is going to be equal to 49.4 degrees. And yeah, it's going to be -2. And you're sitting inside here. There's your theta. And of course, negative because of the quadrant. You can think of it that way. And so what I need to do is find that actual direction angle, which is going to be all the way around. So I'm going to take 360, and I'm going to combine that with that -49.4 degrees, and that's going to give me 310.6 degrees. Now number 12 looks very similar. However, the first thing we need to do is pick out our points. Our initial point is sitting way up here, and so that initial point is at -1 and -1, 4, and our terminal point down here is over at 4, 1. And so now we're going to have to find our magnitude of vectors, or let's go ahead and find component form first. So the component form, 4 minus the -1, and then we're going to have 1 minus 4. Now let's go through and find that magnitude of vector C, and that's going to be the square root of 25 plus 9. So that's going to give me the square root of 34. And then to find our direction angle, again, it looks like we're stuck down here in the 4th quadrant. So we've gone over 5, down 3, theta sitting inside here. And so we need to find tangent of theta equals opposite over adjacent. Theta equals inverse tangent of -3/5. And so here, once we find that angle, we're going to add 360 to it. And so you should get a direction angle of 329.04 degrees. Okay, our last two examples, then we're told to find their vectors are equivalent if and only if they have the same component form. So if they have the same component form, then we're in good shape. So let's look at our component form for vector AB. That component form is going to be -7 minus the -3 and -2 minus 6. And then if we look at the component form for vector CD, well, we're going to have -1 minus 3 and -9 minus a -1. And so these vectors AB is equivalent to vector CD. Okay, now let's look at number 14. Number 14, we look at vector AB. And vector AB in component form, we're going to have 0 minus a -9, -8 minus a -2, so -6. And then we're going to look at the component form for vector CD. And if we look at that one, we're going to have 4 minus a -5, and then 8 minus 2. So vector AB is not equivalent to vector CD.